My name is Tian Xu, and I'm presenting practical urban localization for mobile AR. This project was done during an internship program at ByteDance last summer. Places of interest, or POI, AR applications are emerging. They are widely applicable to urban areas where the merchants proliferate, and the AR effects are specific to the exact camera location and position, and the AR effects are interactively and continuously rendered in real time. POI AR could open a new door to deliver location-related advertisements. For instance, while a user points her smartphone to a coffee shop, the smartphone renders the coffee promotions as a virtual overlay on the wall. POI AR effects can be diverse and are adaptive to existing AR types like marker-based, markerless, and superimposition. For marker-based, the AR effects are overlaid on known physical objects called markers. For example, it can be a QR code. For markerless AR effects, they are rendered in free space. For example, when the user wants to purchase a new type of furniture, she can compare different choices by placing a virtual 3D furniture in her living room. For superimposition, the AR effects provide an alternative view of an object, for example, a virtual overlay aligned on the wall. POI AR needs twofold location information. The first information is a POI label describing the user's current location, for example, a Starbucks. The second information is a 6 degrees of freedom camera pose, which is composed of the camera position and orientation. Current localization solutions are inadequate. For GPS, devices could be blind in urban canyons because the signal transmitted between the device and the satellite can be blocked by those tall buildings, so the localization error can be up to 20 meters. More recently, Wi-Fi-based localization reduces the error to decimeter level. However, it only provides 3 DOF location and limited to indoor environments. Computer vision is a more robust alternative. This is a typical workflow of computer vision customized for localization to support POI AR. At the beginning, the system vendor collects a collection of images ahead of time. Then, the image features will be extracted from the images collected, and the system vendor will store those features into a geovisual database, which relates the geolocation with the corresponding POI features collected. At runtime, given a camera image, the system will compare the similarity of the features from the camera image and the features in the geovisual database to find out the most similar POI. With the POI labels inferred, the system will continuously render the AR effects based on the 6 DOF camera pose. The most representative solution is 3D reconstruction, and it has been utilized in some commercial POI AR solutions. During ahead of time, system vendors collect 2K images per building and extract the visual features like shift from those images collected, and it takes another 4 hours to generate a giant 3D point cloud. At runtime, given a camera image, the features will be extracted and compare the feature points in the 3D point cloud to derive the most similar POI. And the triangulation of corresponding feature points will be calculated to derive the 6 DOF camera positions to support real-time AR rendering. The major advantage of 3D reconstruction is high accuracy, which can reach centimeter level error. However, it requires colossal volume of data collection and expensive 3D point cloud generation. Although it has been adopted by industry pioneers like Scape Technology or Google Visual Positioning System, but they are not scalable to large urban area. So the above solutions mentioned are either inadequate or impractical to support POI AR in large urban areas. GPS is suffered from its high error, and it can only provide 3 DOF position. Wi-Fi also suffered from its limitation to indoor environments, and it can only provide 3 DOF position. For 3D reconstruction, the error is low and it can provide 6 DOF camera position. However, the construction time is super high, so it's not scalable to large urban areas. To this end, We can build an inexpensive localization pipeline with two cheaper and complementary CV algorithms, like image feature matching, which is a low-cost POI recognition technique, and simultaneous localization mapping, or SLAM, which is a real-time 6DoF positioning technique. They are complementary with each other in the composition of the workflow mentioned in prior slide. So our proposal can support both indoor and outdoor environments with low error, and can have real-time 6DoF positions. And both the ahead-of-time cost and the runtime cost is low. The first technique is image feature matching, and it covers the ahead-of-time geovisual database construction and the runtime POI recognition. During ahead of time, the system vendor collects the image data and extract the image features, like SIFT, and store those features in the vocabulary tree. At runtime, given a camera image, the features from the camera image will be extracted and compared with the features compared in the vocabulary tree to find out the most similar POI. The vocabulary tree is a data structure that defines a hierarchical quantization of the features that is built by hierarchical k-means clustering. An initial k-means process is run on the features, defining k cluster centers. In the first quantization layer, the descriptor is assigned to the closest of the three green centers. In the second layer, it is assigned to the closest of the three blue descendants to the green center. All features are stored hierarchically into the tree. SLAM is a localization technique widely used in unknown environments, which derive the camera pose based on the spatial correlation of the corresponding feature points between two consecutive frames. Well-known AR development kits like AR Core and AR Kits are both based on SLAM. So image feature matching and SLAM in tandem can compose the entire workflow. With the help of computer vision techniques, to design a localization system customized for POI AR, we are faced by a few challenges. The first is the high search overhead in the large vocabulary tree, because the search latency grows monotonically with the region size covered. The second challenge is the sensitive data transmission between the device and the untrusted cloud. If the user reveals her own image to the untrusted cloud, it will derive severe privacy leakage. The third challenge is the proportional cost to different AR types and real-world environments. Our first design is to build a vocabulary forest instead of a tree. First, the system vendors will collect tens of images per building that cover multiple positions or angles. Second, the system will detect irrelevant entities like the humans or automobiles or even the trees that do not belong to the POI, and remove the visual features from irrelevant entities detected by some generic object detectors like YOLO. The third step is to index the visual features as a vocabulary forest, which is composed by multiple shallow trees that cover the entire area instead of a monolithic tree. As shown in the figure at the bottom of the slide, we partition the entire region into multiple smaller ones and construct a vocabulary tree for each region. This design overcomes the challenge of the growth of search latency regarding to the size of the vocabulary tree coverage. With smaller trees coverage, the POI recognition by searching for most similar features in the vocabulary tree can be significantly faster with a shallower tree. Our second major design is the incremental tree prefetch. So at the runtime, during POI recognition, the device will prefetch the vocabulary tree from the cloud, corresponding to the region to enter, which avoids severe privacy leakage. And we have few optimizations for this incremental tree prefetch. First, we will prefetch those trees that have a larger overlapped region size between the GPS arrow range and the tree coverage. For example, in the figure, the circle represents the GPS arrow range, which is a 20-meter radius circle, and it has more overlap with region A. So we will download tree A first, and then tree G and tree F. The second optimization is predicting the user trajectory from crowdsourced digital footprints. For example, users may enjoy sharing their POI AR short videos on common social networks, so that the trees containing popular POIs have a higher priority to be downloaded. The third optimization is adaptive tree replacement. Because keep downloading trees will stress the device local storage, so we will replace the downloaded trees by the least recently used policy. Our third design is adaptive 6DoF camera positioning. There are two adaptations. The first one is to adaptation to different AR types. So we have mentioned there are three popular AR types like marker-based, markerless, and superimposition, and they have different tolerance on the localization error and perform delay. For marker-based, for example, if we want to mark a building with its name, it can be tolerated to a few meters error because the buildings are typical buildings are like a few meters wide. And we can have 1 second delay because we don't need to render this continuously in real time. For the second type, markerless, the localization error should be less than 1 meter. And because it's rendering an interactive object in a free space, we need a real-time delay, which is tens of milliseconds. The third type is superimposition, which provides alternative view of an object. The tolerance of the localization error should be less than 10 centimeters. And it is continuously rendered, so the perform delay should also be tens of milliseconds to reach the real-time rendering of AR effects. The second is the adaptation to various real-world environments. So in some extreme cases, the surfaces are distinct, so there are insufficient features to be extracted. So in this case, we can raise the resolution and the sampling rate to achieve a better accuracy in this extreme case. The second is the high camera moving speed. In this case, we can raise the number of features to detect, which will benefit the correspondence of the feature points between two consecutive frames used by SLAM algorithm, so that we can have higher accuracy in this case to compensate the high camera moving speed. We have done some preliminary results. We have done some preliminary experiments, and here are the results. First, vocabulary forest is much cheaper than 3D reconstruction. For vocabulary forest construction, we have an example to estimate a medium-sized city, Palo Alto in California. So for vocabulary forest, we only need to collect 100K images. But for 3D reconstruction, we need to collect 10 million images. So we can save 100x. For the generation time, for vocabulary forest, per building generation time is only 12 seconds. But for 3D reconstruction, the per building point cloud generation time is larger than 4 hours, and we can save 1.2kx. For the storage cost, for vocabulary forest, it's only 1.1 megabytes per building, but for 3D cities, it's 2 megabytes per building. The lower storage cost will significantly reduce the latency of the model prefetch through network and take up smaller storage space on local device. And we can save 20x on the storage. Also, the smaller trees is faster and more accurate. So we have collected 10 images per store on the 11 stores on University Avenue, Palo Alto in California, and we used DBOW2, which is a common vocabulary tree library. So a smaller tree coverage speeds up image matching and reduces the false positive rates. So if we have 4 stores covered, we normalize the latency to 1. And when we have 11 stores to coverage, the search latency will go up 50%. And also, if we have 4 stores covered, the POI recognition accuracy will be 92%. However, with more store covered, there will be higher positive rate, and the accuracy will drop to 80%. In conclusion, we built a practical urban localization solution that supports POI AR, which significantly reduces the head-of-time construction cost, alleviates the privacy concerns, reduces the online user wait time, and adaptive to various AR type and real-world environments. For future work, we plan to expand to a larger image dataset and prototype a tree prefetch in the real world with proposed trajectory prediction, and design demo AR apps to stress test the adaptivity of our system. Thank you.